So what is a catalyst? Catalyst is a substance that you add to your reaction. It's not one of the reagents, and it doesn't get consumed during the reaction. It is simply there. And it is simply there to provide an alternative reaction path, a way of reaching that activated state that we were talking in the previous slides, that is easier to achieve, that is in lower energy. So it's easier for the reaction to happen, so it happens faster. So that alternative reaction path, and we can talk about different what they might do with some real life example in subsequent slides. They are not a reagent, they are not consumed, they are there. They provide an alternative reaction path, a way for those molecules to react and to reach that minimum amount, that activated state in an easier way. So with a path with a lower activation energy. And this lovely image that I've got in this slide from the Argonne National Laboratory is trying to show that sort of artist's impression of how the catalyst works. And the catalyst is this kind of brownish thing you have at the back. And in this case, it looks like a solid catalyst that is there, and the molecules of the reagent is here, and the molecules of the products are here, and here is what is trying to show us, oh, this is the energy barrier, that's the activation energy, that to get them to react, they need to kind of jump over that hurdle. And what the catalyst is doing is giving them, in this case, a place to all meet together, so it's easier for them to react. Different ones will react in different ways, and that's what the image is trying to show you, that you have the reagents and you make the product, and the catalyst is there just to facilitate that process of the reagents encountering each other, and that activation energy, that excited state that will allow you to then make the products, is achieved in a easier, less energetically demanding way. Okay, in the previous slide there was an artist's impression of how a catalyst looks like. Now let's put a diagram on how that might actually look like in a more scientific chemical way. This is an example of the decomposition of hydrogen peroxide, H2O2. H2O2 decomposes to produce water and oxygen. The reaction is thermodynamically favorable. This reaction is spontaneous. It's just extremely slow. It's so slow that one can buy hydrogen peroxide in local pharmacies, and those solutions are perfectly stable. This is a typical example of a reaction that is spontaneous. So yes, thermodynamically it does happen because it's spontaneous. Kinetically, it's just too slow. Unless you use a catalyst. There are lots of things that can be a catalyst. Here I'm just giving an example of bromide and ions. And what bromide and ions are is they help the decomposition of hydrogen peroxide, or H2O2, by providing an alternative reaction path. And here is showing it as a very bumpy ride, that different ones will have a different shape with those graphs. But the point is that, without the catalyst, it takes all this activation energy to the reaction to react. With the catalyst, the activation energy to get the activated reagents is much lower. So the reaction happens faster. And that's what you want when you use a catalyst. You're not changing the thermodynamics, whether the reaction is spontaneous or not spontaneous, exothermic or endothermic, it is what it is. You're changing how fast it's going to happen. Another example of a reaction which is thermodynamically perfectly fine, is spontaneous, exothermic, but is kinetically very slow. The reaction of ethane with hydrogen to produce, this is ethane. This is ethane, this is ethene. So for this reaction to happen at any reasonable speed, you need to use a catalyst. And typically, what you use is a metal, a finely powdered metal. I mentioned here nickel, palladium, platinum. Nickel cheaper, palladium and platinum much more expensive. And that's it. They're finely powdered, and both gases pass through it, and there are interactions between the surface area of the catalyst and the molecules, so it provides a meeting point for those two molecules, the ethene and the hydrogen, to come together and collide effectively. So that's it, that in this case you have a solid catalyst, finely powdered, because you want a large surface area, so it can interact with many molecules at the same time, and it's just a meeting point for those two molecules to meet each other and react. And that provides an alternative path with a lower activation energy, and the reaction happens much faster. Another example of the use of a catalyst, and an artist's impression of how that catalyst might look like, is the reaction of hydrogen and oxygen to make water. A perfectly thermodynamically favorable reaction, spontaneous, exothermic, all sorts of marvelous things, kinetically really slow. You can leave the hydrogen and the oxygen and they won't react, because yes, once they start reacting, it's all fantastic and spontaneous, but the activation energy to get those two gases, those reagents to react, is very high. They are both very stable compounds. They have absolutely no inclination to react with each other. So you use a catalyst. There are also things that you can use as catalysts. And for example, here is the example is platinum. So the sort of blue teal background is the platinum catalyst, and it's a meeting point where the oxygen atoms, which are drawn in red, and the hydrogen atoms, that are the white dots, meet and make water. And you've got the sort of these round circles with the in red and white as the molecule of waters that you're making. You can define catalyst in homogeneous and heterogeneous. In the previous slides, I've shown you examples. I talked about the platinum finely divided, the nickel finely divided, the metal powder as a meeting place of the reagents. That's what we call a heterogeneous catalyst. It's in a different phase of the reactants. Typically a solid, while your reagents are liquids or gases. So the examples I gave you before, and the synthesis of water, from hydrogen and oxygen, or the synthesis of ethane from ethene and hydrogen, I was mentioning powder metals. You can also have homogeneous catalysts, and those are in the same phase as the reagents, and the catalyst is then uniformly distributed throughout the mixture. An example of that was in a previous slide when I mentioned the decomposition of hydrogen peroxide using bromide and ion. So you have the bromide and ion in aqueous solution dissolved in the hydrogen peroxide. So they are all in the same phase. And you can have both, and you can use very successfully both. And there are examples of both types of catalyst in the literature. In the previous examples, and a few more that I'm going to show you in the next slides. Catalysts are an excellent thing. It helps reactions happen faster. And we use catalysts, industrial processes. Nature also uses catalysts, and we'll talk about enzymes in a few slides, and they are excellent. There are also negative examples of catalysts, so it's not always good that they speed a reaction, they increase a reaction rate. And an example of that is chlorofluorocarbons, which are now banned, and the destruction of the ozone layer. So the destruction of the ozone layer can be simplified by ozone, which is the molecule, the formula is O3, to decompose to make oxygen, dioxygen. Let's balance this equation. And oxygen, O2, is a stable form of ozone. Ozone is an unstable one. And in nature, there is an equilibrium in between the ozone and the oxygen. And what chlorofluorocarbons do is they catalyze the the destruction of the ozone, the breaking down of the ozone into the more stable dioxygen. And they are gases. So it's an example of a homogeneous catalyst. And a little bit about biological catalysts, enzymes. Most biological catalysts are enzymes, proteins that act as a framework in which the reaction will take place. They are fantastic catalysts. They enable reactions to occur at normal body temperature, 37 odd degrees, and they increase reaction rates by a factor of 10 to the 6 to 10 to the 12. So they are hugely efficient. As any catalyst, they just lower the activation energy. The final equilibrium doesn't change, delta G doesn't change, it doesn't make the reaction more or less spontaneous, it doesn't make it more or less endothermic or exothermic, it doesn't do anything about the thermodynamics, it's all about the speed of the reaction, because it's about the energy barrier, that activation energy. It provides an alternative pathways that has a lower activation energy, so the reaction goes faster. Typically, a place to meet. Typically you have the enzyme and you have the substrate, and it allows the substrate to meet with, the different substrate to meet, the reaction to happen, and then gets released, and it goes on to react with another molecule of substrate. So they're extremely efficient catalysts that are much better than any catalyst that we humans have designed. They allow the reactions to happen at relatively low temperature, body temperature, and the increase in the reaction rate is huge. Many orders of magnitude. So they're extremely efficient. Another example of the use of catalyst is catalytic converters in cars. So when you burn hydrocarbons in internal combustion engine, you use air, and air is composed of oxygen and nitrogen. Yes, you need the oxygen to react with the hydrocarbons, but the nitrogen will react with the oxygen at the high temperature. To produce nitrogen oxides, which we don't want, they are pollutant, and there will also be a certain amount of carbon monoxide liberated because of the reaction of the oxygen and the hydrocarbons. And if the temperature is not high enough, you will not produce carbon dioxide. That it is a problem in terms of global warming, but it's an inert gas. You will produce carbon monoxide, which is toxic. For example, a Bandit tune engine, or when you start up from cold and it takes you a while to warm up. So a catalytic converter is a place to help that conversion of that nitrogen oxides, which is a pollutant, into nitrogen, and the conversion of the carbon monoxide, which is a pollutant and a very toxic and dangerous chemical, into CO2, which is also a pollutant but it's inert. So here is an example of a three-way catalyst. You've got rhodium and you've got platinum and palladium. So the rhodium absorbs the nitrogen oxide particles, and the platinum palladium mixture embedded in aluminum oxide help split the oxygen. And then you've got a place for the oxygen atoms to react with the carbon monoxide to convert it into carbon dioxide, and you've got a place for the atoms of nitrogen to react with each other to produce N2, and you have a place for the hydrogen of the hydrocarbons and that haven't reacted fully, and the oxygen to produce water. So then you have the sort of mixture of incomplete combustion of your petrol, oxygen from the air, nitrogen oxides made in the combustion process, carbon monoxide made in the combustion process, and fragments of hydrocarbons that haven't reacted fully, and they haven't broken down fully, and the catalyst is there to trap all those molecules and help them get in touch with each other, and to produce nitrogen into CO2 and water.